For decades, Earth's deepest point has seemed to be Challenger Deep in the Mariana Trench, nearly 11 kilometers below the ocean surface. But that certainty is misleading. Over 80% of the seafloor remains unmapped, and even the Mariana Trench is not a single abyss, but a complex maze of basins and ridges. Across the Pacific, equally powerful tectonic forces shape other trenches, raising an unsettling question. Have we truly found Earth's deepest point, or only the deepest we have managed to measure so far? Let's find out. The Mariana Trench lies in the western Pacific Ocean, east of the Philippines and south of Japan, where the Pacific Plate subducts beneath the smaller Mariana Plate. This involves some of the oldest and densest oceanic crust on Earth, allowing it to sink deeper than anywhere else. Within the trench lies Challenger Deep, the deepest confirmed point on Earth, measured at roughly 10,935 to 10,984 meters below sea level. Yet, Challenger Deep is not a single hole. It consists of several adjacent depressions, each separated by ridges and steep slopes. This complexity has reshaped how scientists view ocean depth. The deepest point is not always obvious or fixed, and the Mariana Trench holds its title largely because it has been measured most precisely. The same tectonic forces act across the Pacific Rim, leaving open the possibility that deeper points may exist beyond what we have mapped so far. The Tonga Trench stretches across the South Pacific, east of the island nation of Tonga and north of New Zealand. It is the deepest trench in the southern hemisphere and one of the most geologically aggressive subduction zones on the planet. Here, the Pacific Plate plunges beneath the Indo-Australian Plate at one of the fastest rates observed anywhere on Earth. This rapid convergence creates extreme bending of the oceanic crust, producing a trench with exceptionally steep walls. In some sections, the seafloor drops almost vertically, a geometry that poses serious challenges for sonar mapping. The trench is also associated with some of the deepest earthquakes ever recorded, with seismic events occurring hundreds of kilometers below the surface. These deep focus earthquakes indicate that the subducting plate remains cold and brittle far into the mantle, a condition that allows it to sink efficiently. While current measurements place the Tonga Trench at approximately 10,800 to 10,882 meters deep, slightly shallower than the Mariana Trench, but steep walls and limited survey coverage make precise mapping difficult. Scientists note that if its deepest sections were measured at full resolution, localized depressions could potentially rival or even marginally exceed Challenger Deep, though no such depth has yet been confirmed. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. Running parallel to the eastern edge of the Philippine archipelago, the Philippine Trench is one of the least explored ultra-deep trenches on Earth. It marks a complex subduction zone involving the Philippine Sea Plate and surrounding microplates, creating a highly fractured and irregular seafloor. The deepest known point within the trench, often referred to as Emden Deep, reaches around 10,540 meters, ranks among the deepest places ever measured. Yet much of the trench has never been surveyed using modern multi-beam sonar. In many areas, depth estimates rely on sparse data collected decades ago. Geologically, the Philippine Trench is unusually complex. Instead of a smooth, continuous subduction interface, it contains zones of tearing, bending, and deformation within the subducting slab. This increases the likelihood of narrow, slot-like depressions forming along the trench axis. Because of these factors, scientists consider the Philippine Trench one of the strongest candidates for undiscovered extreme depths. If previously unmapped microbasins exist and were measured precisely, they could potentially register depths comparable to or marginally deeper than the Mariana Trench. The lack of high-resolution mapping means the question remains open, not because of speculation, but because of missing data. The Kuril-Kamchatka Trench arcs across the northwest Pacific, extending from northern Japan toward Russia's Kamchatka Peninsula. It is among the most seismically active subduction zones on Earth and plays a crucial role in understanding deep mantle earthquakes. Here, the Pacific Plate descends beneath the Okhotsk Plate, generating powerful seismic events that can originate more than 600 kilometers below the surface. These deep earthquakes reveal intense stresses within the subducting slab and provide rare insight into processes occurring deep within the Earth. Depth measurements place the Kuril-Kamchatka Trench at approximately 10,500 meters at its deepest point, making it one of the deepest trenches in the world, though still shallower than the Mariana Trench based on current data. However, the trench's depth varies significantly along its length, and its tectonic behavior is highly dynamic. Some geophysicists suggest that during periods of intense seismic activity, flexing of the subducting plate could temporarily create over-deepened zones along the trench axis. If such features were measured at the right moment and with sufficient resolution, they could rival Challenger Deep. These depressions would likely be short-lived, gradually filled by sediment over centuries, making them difficult to observe directly. Northeast of New Zealand lies the Kermadec Trench, a direct continuation of the Tonga subduction system. Its deepest known sections reach roughly 10,047 meters, making it slightly shallower than its northern counterpart, but still among the deepest trenches on Earth. The Pacific Plate here descends rapidly beneath the Australian Plate, producing sharp curvature and some of the steepest trench walls observed anywhere in the ocean. These near-vertical slopes create significant blind spots for acoustic surveys, particularly when older sonar technology is used. The Kermadec Trench is scientifically important because it offers a clearer view of how subduction geometry affects trench depth. Its relatively clean structure, compared to more complex systems like the Philippine Trench, makes it a natural laboratory for studying plate bending and slab dynamics. Scientists note that if the deepest sections of the Kermadec Trench were mapped at full resolution, some localized depressions could prove deeper than current estimates, potentially approaching or marginally exceeding Mariana depths, though this remains unconfirmed. The Japan Trench lies east of Japan's main island of Honshu, with its deepest sections reaching about 8,046 meters below sea level. It gained global attention following the devastating 2011 Tohoku earthquake and tsunami, an event that fundamentally altered scientific understanding of how trenches behave during major seismic ruptures. During the earthquake, sections of the seafloor near the trench axis shifted vertically by several meters in a matter of minutes. This demonstrated that trench depth is not fixed. Instead, it can change abruptly during large earthquakes as the subducting plate flexes and rebounds. Although no measurements after the event exceeded the depth of Challenger Deep, the Japan Trench provides clear evidence that trenches can deepen temporarily under extreme tectonic stress. These changes may persist for centuries before sediment gradually smooths the seafloor. This realization has implications far beyond Japan. It suggests that the deepest point on Earth may not always be the same place, and that transient deeper configurations could exist without ever being observed or recorded. The idea that something could be deeper than Challenger Deep does not rely on the existence of a hidden supertrench. It arises from a combination of geological reality and limited observation. Trenches are not simple V-shaped features, but complex landscapes of ridges, faults, and isolated pits. Challenger Deep itself is part of a cluster of depressions, only one of which currently holds the title of Earth's deepest measured point, and there's no geological reason similar microbasins could not exist elsewhere. Several already known regions, such as the Tonga and Philippine trenches, remain only partially mapped. Beyond these trenches, scientists also point to undersurveyed sections of the Izu-Bonin Trench, the Peru-Chile Trench, and the remote South Sandwich Trench, as areas where depth estimates remain uncertain. These locations share steep trench geometry, limited high-resolution surveys, and active subduction, conditions that allow extreme depths to go unresolved. Sonar technology itself has limits. Near vertical trench walls distort acoustic signals, and narrow depressions can be missed entirely if survey tracks pass even a short distance away. In sparsely mapped regions, the deepest point could simply lie between survey lines. Earthquakes add further uncertainty, as subduction zones are dynamic systems that bend, flex, and rupture, occasionally creating deeper pockets that persist for limited periods. If a point deeper than Challenger Deep exists, it is most likely a small, localized depression within a known trench, overlooked due to uneven mapping rather than geological improbability. The Mariana Trench remains the deepest confirmed place on Earth, with Challenger Deep representing a landmark in human exploration. Yet this confirmation depends on where we have looked and how precisely we have measured. Across the Pacific, trenches such as Tonga, the Philippine, Kuril Kamchatka, Kermadec, and Japan systems experience tectonic forces comparable to the Mariana, leaving open the possibility that deeper points could be revealed with better data. The deepest places on Earth may already exist, hidden within incomplete maps and technological limits. Until the ocean floor is fully charted, the title of Earth's deepest point remains an ongoing scientific challenge rather than a final answer.